5.4 Magnetic effects of electric currents. First equation we have is the force acting on a charged particle moving at some velocity v within B, a magnetic field. The angle between the velocity and the orientation between the velocity and the B field is given by sine theta. So you have a maximum force when the velocity and the B field are perpendicular. Then we have the force acting on a current carrying wire. B is the magnetic field, I is the current, L is the length of the wire within the field, and the angle this force depends on the angle between the B field and the direction of current. Closer to 90, the more force acting on the wire. Okay, the magnetic force can be demonstrated using two-bar magnets, which are metallic bars. They have north and south poles. Like poles repel, unlike poles attract. This is called the pole law. Because of the historical use of compasses for navigation, magnetic poles of these detection devices are defined like this. The pole labeled north is really the north-seeking pole. It is polarized north, so that and likewise the pole labeled south is really the south-seeking pole. So as it turns out from the pole law, the north geographic pole is actually a south magnetic pole. Isn't that interesting? So again, the north-seeking pole just means that the north pole of the hanging valence magnet in a compass points towards the north geographic pole of the Earth, which happens to be oriented south. The field lines along which the magnets align themselves are the magnetic field lines. B is a symbol used to represent the magnetic field, also known as the magnetic flux density. We go into greater detail on flux in topic 11.2. So the B field is measured in units of Tesla, and the B field is a vector. So magnetic flux density is the magnetic field. It is a vector because it has an orientation and a magnitude. Okay, by convention, the direction of the magnetic field lines is the direction a north-seeking pole would point if placed within the field. So just as in any field, the strength of this B field is proportional to the density of the field lines. So the more field lines that are depicted, the stronger the B field. At either pole of the Earth, the B field is the strongest. That's where all of these lines are converging. Okay, so a bar magnet is a magnetic dipole because it has two poles, north and south, di meaning two. Compare the field lines of the magnetic dipole with the electric dipole, which also has two poles, positive and negative polarity. So we can see that this would be a magnetic field, a magnetic dipole, versus an electric dipole. Externally, they are identical, so how do they differ internally? So for an electric dipole, it's possible to split the dipole into its constituent monopoles. You can separate the two charges, and independently, a negative electric monopole and a positive electric monopole can exist. So we can easily split electric dipoles into their monopole constituents, but can we do the same thing with magnets? Is it possible to cut this magnet in half and have just a south pole across the entire length of the object and a north pole across the entire length of the object? Well, every time you try to split the magnet, all that happens is a new magnetic field forms on the end that you split, on the cut end. So in truth, it's not possible to isolate the poles on a magnet. No one has succeeded in creating a magnetic monopole, but if you do, you discover one, you'll most likely win a Nobel Prize and you'll be rich and famous. So consider a current carrying wire as shown. When current travels down the wire, a magnetic field encircles the wire all along the length, going in a circle. And if the direction of the current is reversed, the direction of the field circling it also reverses. Okay, so we are going to now learn the right-hand rule for the magnetic field direction around a straight length of wire. You point your right hand, the thumb on your right hand, in the direction of the current. So look at the picture, point your thumb down. Wrap your fingers then curl around the length of the wire. And as your fingers curl around, you should see on the left-hand side of the wire, your fingers would go into the board or into the page. And they circle back underneath, and on the right-hand side, your fingers would come up out of the screen. That is how we determine the orientation of the B field around a straight length of wire with current traveling down. Okay, so drawing things three-dimensionally on a 2D plane isn't easy. And so here are the conventions for drawing B fields. So if a B field, we draw things, vectors, using arrows. So if you can imagine you're looking at an arrow, and if the arrow was coming on at you, you would see a point, a tip, the arrowhead. If the arrow was a classical arrow and had feathers on the back, you would see a crosshatch, like an X shape for the tail feathers. So if you're looking dead on at the arrowhead and the B field is coming at you out of the screen, you would draw a point or a dot. Here it's represented a dot with a circle around it, but you will also see it just represented as a dot. If you're staring again at the tail, you would see an X for like a tail feather. Again, you don't have to have the circles around the symbols. Most of the time you'll just see the dot for the tail, the dot for the head of the arrow, and the X for the tail of the arrow. If you see the dot, the B field is coming towards you. You see the X, the B field is oriented away from you. Okay, so using the drawing conventions just shown, we're going to sketch in the B field for the current carrying wire shown here. Again, your thumb points in the direction, your right thumb points in the direction of the current, so to the right. Your fingers then curl around the wire. What is the direction of the B field in this region above the wire? So what is the direction of the B field, the magnetic field, here? And if you've done it correctly, it should be out of the page toward you, or out of the screen. Okay, and so to represent that, we use dots. We're staring at the head. Sorry, it's kind of hard to make dots. Okay, you can probably do this better on paper. All right, now your fingers have curled up and over, and they go back into the page on the bottom, and so that would be represented using X's. And that's how you draw a B field around a current carrying wire. Now you can make a loop of current by taking a straight wire and wrapping it around into a loop, which is what is done in turbines and other plants that manufacture alternating current. So you can take this loop and just bend it. And you'll see in the middle of the loop, the B field gets really concentrated. Less concentrated outside of the loop. All right, this level of physics doesn't require derivation of the two formulas, but I encourage you to add them to your data booklet under topic 5.4. The odds of you being tested on this, I haven't seen, but I did notice in the front of the data booklet, they give you the permeability of free space symbol, the mu naught. So I'm just going to include this in case. So we have the magnetic field strength, a distance d from a current carrying wire. B is the magnetic field strength. Mu naught is the permeability of free space. I is the current, divided by 2 times pi times the distance. And then we have the magnetic field strength in the center of a current carrying loop of radius r. B is mu naught, which is the permeability of free space times I over 2 times the radius. Again, mu naught is 4 times pi times 10 to the minus 7 Tesla meter per ampere permeability of free space. Epsilon naught, 8.85 E negative 12 Coulomb squared per Newton per meter squared is the permittivity of free space. Permeability, permittivity. Ugh. So in similar fashion, the magnetic field direction for a wire loop is also determined using a right-hand rule. This is a little different. So place the heel of your right hand, and by the heel of your right hand, I mean the edge of your right hand along which your pinky also lies. So look at your pinky, and all along the right hand side of your right hand, that is the heel of your hand. So you are going to place the heel of your right hand on the loop, in the middle of the loop, on the plane of the screen in such a way that your fingers then curl in the direction of the current. So right now I have my hand, my right hand, the right hand side of my right hand facing down towards the page or facing away from me. My fingers are curling in the direction of this red arrow, and my thumb is pointing up, back out, is pointing towards me. I know this picture is not represented very well, but it's really hard to show 3D on a 2D plane. My extended thumb, your extended thumb, pointing at you, is in the direction of the B field. You could also just use the straight wire right-hand rule and grasp the loop itself if you would like, and you should obtain pretty much the same thing. Thumb points in the direction of the B field, fingers curl in the direction, thumb points in the direction of current, fingers then curl in the direction of the B field, and you end up with the same thing. This right-hand rule that I've just shown where you place your heel will tell you the orientation of the magnetic field inside the loop. All right, a solenoid is just a series of loops stretched out as shown. So the right-hand rule for this one is you curl your fingers around the solenoid in such a way that it matches the direction of current in the loops. So I have current coming up on the right-hand side. It goes up like this and down on the back side. It is up. The direction of current on the front of all of these loops is oriented up. On the back of the loops, away from me, the current is oriented down. So down on the back, away from the screen, and up on the front of the screen. So if I curl my fingers in that direction, up on the front, my right hand, my palm is currently facing away from me, my fingers are going up, and they curl over on the back side of this solenoid, then my thumb points to the right. So the direction of the magnetic field from this solenoid is this way. So here is a better depiction of what the B field looks like around a solenoid. Remember that Sandy Claus flies out of the North Pole in the same way the electric field lines come out of the north, and they fly and they are oriented into the south. So Santa flies out of the north, just like the field lines also come out of the North Pole. If an iron core were placed inside of the solenoid, what we would have is called an electromagnet. The magnetic field of the solenoid would induce a magnetic field inside of the iron, turning it into a electromagnet. The ferrous core would enhance the strength of the B fields, and this is how you can generate some really powerful magnets on Earth. All right, in the solenoid shown, label the north and south poles. Okay, so the trick with this is using conventional current to determine first the direction of current. So the question is, does current travel left or right through the solenoid? So this is the solenoid. Is current going this way or is it going this way? And if you said current travels to the left, you are correct. Current comes out of the positive terminal and into the negative terminal. So this is the overall direction of current. So let's label the front side of the solenoid to determine what way it goes. So current comes out like this, down the back side of the solenoid, and so the current is traveling up along the front. So my fingers need to go up, and then they would curl over and around the back of the solenoid. So that means the thumb on my right hand points to the left. Right thumb is pointing left. Curl your fingers if you haven't already done so. Your fingers represent the current. Thumb is pointing to the left. So that means which end of the solenoid is north? The north end would be here, and the south end would be the opposite. So, a moving charge placed in an external magnetic field will feel a magnetic force because of the pole law. So really quick, remind yourself, what type of fields do charges create? A stationary charge, that means a charge that's not moving in a magnetic field feels no magnetic force. The charge doesn't make its own magnetic field, it makes an electric field. So if the object, if the proton or the electron is stationary, there is no magnetic force. It's only when these charges start moving do they experience a magnetic force. And that's a really interesting phenomenon. The force F felt by a charge Q traveling at velocity v through a B field of strength B is given by F equals QVB sine theta, where theta is the angle between the velocity and the B field. All right, so now we are going to use a right-hand rule that's a little harder, but it's not that bad. This right-hand rule will allow us to determine in what direction is the force acting on a charge moving in a B field. So you take your right hand, and this works only for positive charges, only for protons or cations moving. You use your right hand for these. So the direction of the force, I always start by pointing my fingers in the direction of the B field. Typically, the B field is given. Typically, in a mass spectrometer, the B field is set up such that the scientists know where the B field is. It's the first thing you know. So you know the direction of your B field, fingertips point in that direction. Your thumb points in the direction of the particle's velocity. So where was that object traveling? Along what line? You keep your fingers pointed in the direction of the B field, and then you can flip your hand over or sideways, back and forth, to get your thumb in the direction of velocity, just like we would put our thumb in the direction of current. The palm then, the face of your palm, points in the direction of the force on the particle. I feel like using the right-hand rule with a flat hand rather than using your index finger and your middle finger and your thumb is easier. But in truth, you can use either types of right-hand rules if you look online. In this case, if you use the middle finger, forefinger, and thumb, the middle finger replaces the face of the palm. but I think keep your hand flat like you're going in to give someone a handshake. Fingertips point in the B field direction. Thumb points in the direction the object was traveling in, and the face of your palm points in the direction of the force that the object experiences. If then you are dealing with free electrons, not electrons moving down a wire, but electrons that are just moving independently in a field, you then do the exact same thing but with your left hand. All right, question number 3. A 25 microcoulomb charge traveling at 150 meters per second to the north enters a uniform B field having a strength of 0.05 Tesla and pointing to the west. What will be the magnitude of the magnetic force acting on the charge? So we are going to use the equation from topic 5.4 for a charge moving in a magnetic field. F is equal to Q times the velocity times B times sine theta. And we need to figure out what is the angle between the B field and the velocity. So let's see. Set up our coordinate system. North, south, east, west. So what's the angle between north and west? Well, that's 90 degrees, so we have a maximum effect. Sine of 90 is 1. So plug in, make sure to convert as necessary, and get the force, just the magnitude. Now, which way will the charge be deflected? To know this, we need to first figure out, is this a positive charge or a negative charge, and what hand, the right or the left, do we use for this? Well, it's a positive charge, so we do use the right hand. I like to start by pointing my fingertips in the direction of the magnetic field. So the magnetic field is oriented to the west. That means I will point my fingertips point left. The fingertips on my right hand are pointing left right now. Now I take my thumb and I'm going to point it in the direction of the velocity. The charge is traveling 150 meters per second to the north. So the fingers on my thumb are pointing up. I'm sorry, the fingers on my thumb. My thumb points up. And so let me draw what this looks like, what I have. My hand is like this. It looks totally like that. And then my thumb is pointing up. And then my palm is facing towards me. So this is the face of my palm. Okay. My palm is facing me. So that means that the charge is deflected out of the page. Since you're writing on paper, it makes sense that that charge would be coming out of the page towards you. Okay, so explain why the magnetic force cannot change the magnitude of the velocity of the charge while it is being deflected. It's a really great point. And the reason is because that the force is perpendicular to the velocity. It cannot change the magnitude. It cannot change the magnitude of velocity, only the direction. This is a lot like the centripetal force. So let me explain. We had a charge, a positive charge, and it was originally moving north. At the same time, this magnetic field was acting on it to the right. That means then that the force that arises is coming out. So instead of just moving suddenly to the right, what the proton or the positive charges will do is like arc out in a circle. Just like the moon encircling the earth, there is a force perpendicular to its instantaneous velocity direction, And because the force is perpendicular to the velocity, it can't change the size of that vector, but it can just cause it to rotate around. So these charges end up moving in like semicircles, in like an arc around in the magnetic field. So how do we know that the charge will be in uniform circular motion? Because the velocity magnitude is constant. The B field strength doesn't change. And the direction between them is at an angle, and the orientation between these two are perpendicular. We know that the charge continues in a circular path at constant speed. Circular path at constant speed. Something to that effect, because this is the way moving charges behave in a magnetic field. They act as though there's a centripetal force guiding their motions, and they display circular motion behavior. Okay, and part E, if the charge has a mass of 2.5 e negative 5 kilograms, what will be the radius of its circular motion? Well, if you go to topic 6, which is on the same page, you should see topic 6.1, circular motion. We have this equation, F equals m v squared over r, and r is the radius that you'll be looking for. An electron traveling at speed v perpendicular to a magnetic field of strength v experiences a force F. What is the force acting on an alpha particle traveling at 2v parallel to a magnetic field strength of 2b? So you might be inclined to say we need to set up an equation, F is equal to Q times V times B sine theta, and compare the two. Just so you know, the alpha particle is a helium nucleus. Alpha is helium nucleus. Hydrogen has 1 proton plus 1 charge, or the nucleus of hydrogen plus 1. The nucleus of helium has plus 2 charge. So alpha particle, you will need to know this, as plus 2 e charge. However, some very important information, the angle. The velocity and the B field for the alpha particle are in the same direction. They're parallel. Sine of 0 is 0. So there is no force acting on the alpha particle. Alright, so we already know the effect of a magnetic field on a moving charge, and it stands to reason that a wire carrying current in a magnetic field will also feel a force, because charges are moving throughout it. Current is moving charge. So a wire with no current feels no magnetic force. So imagine I have a wire and it's within a uniform B field. But a wire with current will be deflected by a magnetic force as shown. Depending on the direction of current, this deflection will change one way to another. Knowing the right-hand rule for a charge is all you need to know to determine the direction of the force in the wire. So I've tried this experiment. Maybe I'll have better success this year. I've tried to measure the deflection of wires carrying current, 2 wires next to each other. I haven't been able to get noticeable effects, but I really haven't had time to invest in proper design, and maybe one of you guys is interested in doing something like this for your IA. There are so many great IA topics, IA ideas out of topic 5. It's really, you should consider it. Okay, so we now know that the direction of the magnetic force acting on a current carrying wire, if it is in a magnetic field, can be determined using the right-hand rule. The magnitude of the magnetic force, F, acting on a wire of length L and carrying a current of I in a magnetic field B is given by this formula, F equals BIL sine theta, where theta is the angle between I and B. This is the force on wire of length L due to an external B field. Remember, the wire is going to generate its own B fields, and the two B fields, the one around the wire and the one external, will interact with each other, causing deflection. Question 5. A 25-meter long piece of wire carrying 15 amps of current to the north is immersed in a magnetic flux density of 0.076 Tesla, which points into the page. Find the magnitude and direction of the magnetic force acting on the wire. So let's start by drawing this wire. Long piece of wire with current going north. And there is a magnetic flux density, that is a B field, which points into the board. So if it's pointing into the board, do I draw X's or do I draw dots? And if you said dots, you're incorrect. It's X's. The last thing we see are the tail feathers of the B field as it's pointing into the page. So find the magnitude and direction of the magnetic force acting on the wire. I'm going to need to draw the magnetic field around the wire. And remember, the north field lines are attracted to south field lines. South field lines are attracted to north field lines. So using your right hand rule for current down a wire, you point your thumb in the direction of the current again, fingertips curl around the wire. So if you've done this correctly, you should get the B field for the wire itself coming out of the board like this, or out of the paper, and then into the paper here. So on this side, it's like having two south poles next to each other. And on this side, it's like having a north and a south. So the right side of the wire feels repulsion with the magnetic field. The left side of the wire is attracted to the magnetic field. So the wire moves this way to the left. So then all you're left with doing is calculating the magnitude of the magnetic force acting on the wire using the equation F equals BIL sine theta. Okay, so no discussion of electromagnetism is complete without making mention of James Clerk Maxwell, who is a Scotsman from the late 1800s, and he deduced that the electric fields, and magnetic fields were two sides of the same coin, that there was something called an electromagnetic wave, and he wrote a series of equations called Maxwell's equations for electromagnetism, continuing the work of Gauss and others in the field. Really, he was brilliant. He deduced the speed of light to like 6 decimal places or 6 significant digits of precision before there was any way to measure it. These are just a few of the equations that he used, and you'll see the permeability of free space and the permittivity of free space. He was without a doubt brilliant. But you can see this GIF shows you how an electromagnetic wave, like a wave of light or anything from the electromagnetic spectrum, contains an oscillating electric field and a B field. We'll go into more depth on this in topic 4. Okay, 6a, a connecting wire in a circuit has a radius of 1.2 millimeters and the current in it is 3.5 amps. The number of electrons per unit volume of the wire is 2.4 E28 meter per cubic meters. Show that the drift speed of the electrons in the wire is 2.0 E-4 meters per second. Oh, drift speed, huh? Well, we're going back. This is a throwback to topic 5.1, topic 5.1, if you should remember, I equals N times A times V times Q, where N is the number density, which is this right here, the number density, number of electrons per unit volume. That's the number density. We have the radius of this wire, and we can assume that the wire is circular, so we can get the cross-sectional area, which is essentially the area of a circle. You'll need to convert 1.22 millimeters to meters, and you should remember the area of a circle is pi r squared. And you have current, which is 3.5 amperes. And we are going to solve for V. Where do you get Q? Well, these are electrons. The value for the electron is 1.60 E negative 19 Coulomb. Hopefully, if you've set everything up correctly, you will get that the drift speed, the velocity, is around that. Alright, the diagram shows a cross-sectional view of the connecting wire in A. Determine the magnitude and direction of the magnetic force on one of the charge carriers in the wire. So I know there are electrons moving in the wire, but as I told you before, if you're dealing with wires at all, you still only use the right-hand rule. The only time you'll use the left hand is if it's just a free electron inside of a field. Okay, so look at how the current is depicted traveling in the wire. It's into the page. Hey, they even told you. Into the page, so your right thumb points in. Fingers curl around the direction of the wire itself. If you've done this correctly, you'll see that the direction of the magnetic field around the wire is clockwise. So it goes down, around like this, up, and back over. And I've labeled the direction of the field at 4 points around. Now, look at these 2 points on the left and right hand sides. Notice that the direction of the field, the B field produced by the wire, the B field produced by the wire is in red. The B field, the external B field is black, the black arrows drawn. If the B fields are perpendicular to each other, as shown on the left and right hand sides, there's no interaction there. It's only when they're aligned, when they're pointing in the same direction, will you have an effect. Okay, so I don't have to worry about the wire moving left or right. Wire does not move left or right. Okay, so we don't have to worry about left or right. So focus on up and down, because those B fields are actually parallel. So this B field up top points in the same direction. The 2 B fields above the wire point in the same direction. That's like having 2 north poles next to each other. But if you look at the B field on the bottom, the external magnetic field points to the right. The B field from the wire points to the left. These are opposite directions, so it's like having a north and a south pole together. As such, the entire wire feels a force down. You're left now with calculating the magnitude of the magnetic force. On a wire, be sure to use the correct equation. A beam of electrons moves between the poles of a magnet. What is the direction in which the electrons will be deflected? Okay, so first let's go ahead and draw the direction of the magnetic field between the ends of the magnet. Remember, Santa Claus flies out of the North Pole in the same way the field lines come out of the north and go into the south. So this is a beam of electrons, and these electrons are not associated with a wire. So are we going to use our right hand or our left hand? We're going to use our left hand for this. Okay, so fingertips on your left hand point to the right. So out of the north into the south along the green arrows. Now your thumb is going to point in the direction of the beam of electrons. So fingertips point in the direction of the green arrow. Your thumb on your left hand points in the direction of the red arrow. And the face of your palm points in the direction of the force acting on the electrons. So the direction of this force tells you the direction the electrons are deflected, and if you've done this correctly, you should get the right answer. Question 8, 2 current-carrying parallel wires are kept in position by a card with 2 holes in it as shown. In diagram 1, sketch in the force acting on each wire. So if there is a force of repulsion between the 2 wires, you should label it like this. There is a force of repulsion if the orientation of the B field between these two are in the same direction. So imagine that these 2 circles I've drawn are actually like flat down, like here along the card. And if the 2 B fields in between happen to point in the same direction, there is repulsion. If you determine that there is attraction between these two, you can draw the forces like this, F1, F2, and the B fields, if there is attraction between the 2 wires, they should be oriented in the opposite direction. Okay, so I leave this one for you to decide. 2 current-carrying parallel wires are kept in position by a card with 2 holes in it as shown in diagram 2. Sketch the magnetic field lines in the card produced by the 2 wires. Good luck with this. I hope you learned a lot, and thanks for watching.